Okay, hi everyone, I'm Marco Russo. Today I will tell you a story which has this very long title, and it's basically about the usage of neutral atom quantum computers for a specific subset of machine learning algorithms called support vector machines. And in the specific case, what we do is called quantum kernel estimation. Now, this is the first work that uses neutral atom quantum computers to do this, and specifically with a gate-based approach. So before proceeding, I will start with a quote. And this quote says that the atoms may be small, but their contribution to machine learning might be monumental. Now, the funny thing about this quote is that it's not by me or from some other scientist, but it's actually by this guy here. So this is basically machine learning, talking about machine learning, so I don't know how much we could trust it. But even though monumental might seem a bit too much, I think that neutral atom quantum computers might have some serious advantages that we can exploit in a very good manner for this problem. So, first of all, how can quantum computing be exploited for machine learning? Because this is not obvious at all, you know. And above all, is it better to try to do exactly what classical machine learning already does perfectly and to replicate where it is already very well performing? Or instead, should we try and figure out what only quantum computing can do, and instead classical machine learning cannot replicate? Well, I think that it might be more challenging, but also a bit more satisfying to follow the second path. So to exploit the unique features of quantum computing and not trying to replicate what the classical structures already are in machine learning. So we can think about kernel SVM as when we have a set of points belonging to the Euclidean space with f features. So f now is the number of dimensions. And this point belongs to a class. And this class is defined by a label, which is either +1 or -1 in this case. So the training set is the set of all the points that we use for training, and instead the test set is the set of all points that we use for testing. And of course, the machine learning algorithm doesn't see the test set during the training stage. So what we do is that since we want to separate this data with a hyperplane, and since they are not always separable linearly, we bring this data into a higher dimensional space by means of a feature map that goes from the original space to a feature space called F. So this feature map is phi, and what happens here is that if we define a kernel function as a function that takes as input 2 data points and takes as output the inner product of these points in the high dimensional space, now what happens is that if we define the kernel training matrix as the matrix whose entries I and j are the kernel function calculated between every possible couple of the training set, then learning corresponds to optimizing this function here. Now, I know that this looks like a mess. For the ones of you that have never seen SVM, this might look like nonsense, but I just want you to focus on the fact that learning doesn't involve the calculation of the feature space at all. So here we just have Km, which is just the inner product. And it turns out that sometimes calculating the inner product into a high dimensional space is way faster than first calculating the feature map and then performing the inner product. So now to test, we define the test kernel matrix in the same way, and the classification is done calculating again this quantity here that once again doesn't involve the feature map calculation at all. So in 2021, IBM published a paper that tried to apply superconducting quantum computing to this problem here. I took this paper as an inspiration to use as a starting point for my work. So I used 3 features, and what we have is that we have a fixed feature map phi, then we choose a fixed random unitary v belonging to the special unitary group 8, then given the observable z1, z2, and z3, and for every random generated point belonging to the 0 to pi cube, then we assign a label to this point. And this label is +1 if some condition is satisfied over this point, else it's -1. What is this condition? The condition is that the expectation of that observable when we apply the random unitary to the feature map of that point, if it's greater than or equal to delta, then it's +1, else it's -1. So, of course, we need a circuit that performs this mapping, and this circuit is this one. This is the unitary. This is very complicated, but later we will see how it takes form for 3 qubits. So now let's forget about the dataset generation. Basically, we use a quantum computer to perform the calculation of the kernel. How do we do this? Well, we need a feature map again, and we will use the same feature map that we used for dataset generation. Now, I know what you're thinking. Hold on to that thought for a second, because we will see it later. We apply this feature map to the initial state, all zeros, and we get the feature map in 9 dimension of the initial state. So we have this circuit here. And instead of using state vectors, we will use the density matrix. Why? Because when we perform the inner products, we want to not think about the global phase. So if we use the density matrices, then the kernel is calculated as the distance between two matrices, which is the Frobenius inner product, which in this case, since the density matrix is calculated like this, then the inner product is the inner product of the two state vectors elevated to 2. So this is equivalent to first apply the feature map of x1, then the inverse of the feature map of x2, and then calculating the probability of getting 0 and elevating it to 2. So we need this circuit here. This way, we can estimate the training kernel matrix, so that for each pair of the training set, we perform n shots of this circuit, and then we can estimate the empirical probability of obtaining 0, so that we can calculate the entry of the kernel matrix. Of course, the higher is the number of shots, the least is the standard deviation, because it decreases with 1 over the square root of n. So the same is for the test kernel matrix, but about the thought that I was telling you to hold. The same mapping that we used for generation was used again for training. So is this like cheating? Because we are introducing in the training stage something that maybe you shouldn't know. Well, actually, let's talk about what does the mapping define. The mapping defines how the high-dimensional space that we bring the features into is shaped, okay? Instead, the unitary V that is unknown during training, that's what defines how the value of each resulting feature in the high-dimensional space determines the class. And the training stage doesn't know this, so it's not cheating. Now, about the 3-qubit feature mapping unitary, we can immediately see that here every qubit is entangled with every other qubit. Now, this might not seem like so much of an issue for just 3 qubits, but the problem is that if we are forced to entangle every qubit with every other qubit, then just for 100 qubits, which is not a high number at all, it's actually very, very low, we have a total number of 100 choose 2, which is approximately equal to 5,000 pairs. So this means that we have to introduce a lot of swap gates, as we will see, if we have superconducting qubits. Because the problem here is that this procedure is not scalable with superconducting qubits. Why? Because this is basically, these are some standard layouts for superconducting qubits, and we can see that even in the best case, a qubit is at most surrounded by 4 neighbors. Now, this means that if you want to entangle every qubit with all the other ones, we are forced to introduce a lot of swap gates. So the circuit depth increases hugely, and I don't think this is the right time to have very long circuits because of the coherence. So why shouldn't we use instead a neutral atom quantum computer? Instead of having a fixed layout, we can actually decide ourselves how we can move the atoms around. So what is a neutral atom quantum computer, first of all? Well, we have rubidium atoms which are controlled with laser pulses, and as we can see here, the shape, the arrangement is arbitrary, so we can decide it. And what this means is that where with superconducting quantum computing we adapt our circuit to the hardware, here instead we can adapt the hardware to the circuit, which is a huge advantage in my opinion. So here, as I said, the mutual position is not fixed, and it can be rearranged at each execution. So now, talking about the atom arrangement, and now we can exploit this. If you think about the 3D space, now let's imagine a cube which has length 2D, okay? Now, if we divide this cube into 3 sections, so top, bottom, and center, now let's think about the center one, and let's think about the atom in white, which is at the center of this cube. Well, we know that basically the minimum white and blue distance is equal to d, and the maximum distance is d times the square root of 3. So this means that if we replicate this cube in space, we obtain a lattice of atoms where each atom is surrounded by 26 possible neighbors. So we went from 4 neighbors to 26. This allows us to reduce the depth a lot because now we need many fewer swap gates. And of course, I mean, to find the optimal sequence of swap gates anyway is of course an NP problem, but this is not the focus of this paper here. But now, I mean, solve this problem, I should speak about computational paradigms in neutral quantum computing. We have the analog paradigm, which is when we encode the problem as a Hamiltonian. So we start from an initial state, then we make the system evolve following the Hamiltonian that encodes our problem, and then the solution is the final state after this evolution. But the problem of this approach is that it's only good when we either want to do quantum simulations, for which we already have a Hamiltonian, or easy to encode machine learning problems like QAOA. And this is massively used in neutral quantum computing. Instead, the digital one is when we encode a problem as a gate circuit, and this is actually the standard computational model for which quantum computing was born. This allows us to represent way more efficiently complex problems, or to represent them at all. And this is a much less researched area in neutral atom quantum computing, to the point where in Pascal, for instance, we even have a missing gate library. So my goal was to pass from the theoretical representation here, so high level on the left, to an actual sequence of pulses that correspond to that circuit. So a method to get a pulse for each possible unitary, achieving universality, was needed. This allows us to implement the quantum kernel estimation directly using the gate model. So the first part of my work was to achieve this. I used the Pascal CheDoc2 device, which is a simulator with these constraints here: a maximum amplitude, a maximum detuning. The detuning is just the difference between the frequency of the pulse and the frequency spacing of the two energy levels. And then the minimum time between retargets, which is, since we use a local channel, there's one idle time when we switch from one qubit to the other. And this is approximately equal to 0.2 microseconds for this case. This is how I decided to arrange the atoms into the space, so like a triangle, and we have that maximum distance is 4.5 micrometers. And on this device, only 2D arrangement was possible, but it's likely that in the future we'll be able to simulate also 3D arrangements. Okay. So controlling a 1 qubit, and especially having a 1 qubit gate, basically means performing a rotation on the block sphere. So if we use the local Raman channel, we have two levels, the ground level and the hyperfine level, so 0 and 1. This is the pulse Hamiltonian, so this is the drive Hamiltonian, sorry. And it may look very complicated, but it just tells us what we can control about the pulse and how the pulse affects our system. And we have three parameters for this pulse. We have the amplitude, the phase, and the detuning. Now, with this Hamiltonian here, we obtain a rotation along an arbitrary axis, which is only determined by phi and lies on the equatorial plane on the Bloch sphere by an angle theta, which is equal to the integral of the amplitude. And the result is that since the amplitude is usually the Blackwell window function, where A is the maximum amplitude and T is the pulse duration, we have that the duration of the obtained gates, which only depends on theta, is given by this formula here. And since we have a constraint on A, which is the omega max, this is a plot that shows how the angle affects the duration. So the maximum duration is when the angle is equal to 2 pi, and it's approximately equal to 0.25 microseconds. Now, instead, for 2 qubit gates, we use the local Rydberg channel, where we have an additional level, the Rydberg level. This channel here allows us to have the so-called Rydberg blockade effect that allows us to have entanglement. This is a Hamiltonian that just shows us how there are van der Waals interactions between neighboring atoms. It's a very weak interaction to the point that its force decreases with the 6th power of the distance, so they have to be very close. And in the Pascal paper, it was shown how to exploit the Rydberg blockade effect to obtain a CZ gate with a pi to pi pulse sequence. But we want a CX gate. How do we obtain it? First, since the 2 pi pulse performs the Z operation up to a global phase, the control is 1, then the Rydberg blockade must be possible during the 2 pi pulse. And this means that the radius, so the distance between the two atoms, must be strictly less than the Rieber blockade radius, which is inversely proportional to omega max. And this means that the farther they are, the less must the amplitude be. And what about Cx? Well, since we know that X and Z are actually similar by means of a basis transformation, and more specifically the Hadamard base, then we can just do this. Before and after the 2 pi poles, we can switch to the Raman channel and perform NH poles. Now, the results are that if we impose a conservative radius equal to 10 micrometers, we have that the maximum amplitude for the 2 pi poles is equal to this, which makes the 2 pi poles much longer than the ones for the pi before and after. So we can say that the duration of the Cx gate is approximately equal to the duration of the 2 pi poles, which is equal to 2.76 microseconds. These are just numbers. But what about the results? Well, the dataset was generated with 3 features, as I said earlier. We have 40 training samples and 20 test samples. And the margin of separation was 0.1, so it was really low. And just to give you an idea of the complexity of what the classifier has to learn, this is what the dataset looks like. So in red, we have a class. In blue, we have the other class. And even to us, this looks like just random noise. So the results are that this is the pulse sequence for the feature mapping circuit for 2 random points. So this gives us an idea of the average duration of the sequence, which is approximately 80 microseconds. This is the heat map of the training kernel matrix, where of course the entries on the diagonal are 1. And we obtain that the test accuracy is 0.75. Now, this might not look like a lot, but the interesting thing is that if we take a classical kernel instead, then the accuracy is 0.65. Now, this is very interesting, in my opinion, because we only have 3 features. So the quantum algorithm beats the classical one even with just 3 qubits. And this is interesting because we are so used to the thought that we need millions of qubits to obtain a quantum advantage, that this is the proof that sometimes even just 3 qubits are enough. So it's evident that for some problems, it's not a matter of numbers of qubits, but it's more about the fact that with quantum, we can get relationships that a classical computer can't. So in conclusion, first, a universal gate library was obtained for any possible neutral atom device. So this can be used for anything. The quantum kernel estimation algorithm was implemented for the first time with a fully digital model instead of an analog one. It was shown that it beats classical kernels even with just 3 qubits. The 3D arrangement can be used for future work, of course, when the simulations will allow us. And of course, to decrease the gate duration, since it's inversely proportional to omega max, then we need to have channels that allow us to have higher amplitude, of course. And this advantage here of neutral atoms, that is to say the rearrangement, can actually be used for everything. So not just the quantum kernel estimation. So whenever we need to entangle a lot of qubits together, we can just use neutral atoms to exploit this advantage here. And since the circuit depth is massively reduced, this is where it comes from. And the last point is that, okay, this was an artificial dataset, so this was generated for the quantum computing to make sense to apply to this. But I think that even though the scenarios of interest are yet to be explored in real life, let's say, I think that, first of all, quantum data inherently have these kind of relationships that can benefit from this. And I also think that every real problem that is not quantum, but which has data with features that are strongly dependent one on the other, can seriously benefit from all of this. So yeah, I'm done. Thank you.
Hi, thank you for the nice presentation. I'm Mark Oliver Wolf from Fraunhofer ITWM. So I'm wondering, how did you check that your results were not just dependent on some local optimum?
Yeah.
And that could be because your optimum of your optimization problem for the machine learning.
No, of course, this was just the result of some cross-validation and changing the hardware parameters. So it was seen that it always converged to that optimal, let's say. So yeah, it was checked.
So did you play around with the initial parameterization?
Yeah, of course.
Okay.
Yeah.
Thanks.
Thank you.
Hi, thank you for the great talk. I would like to ask if you could repeat like how you transfer like the gates into the hardware, like because I think
into pulses, you say?
Yeah, because I think you mentioned like the C set that you implemented it on hardware.
You're talking about this?
Yeah.
Okay, yeah. This is the Hamiltonian of the driving pulse. So it means that this is the potential that corresponds to the fact that we are using laser pulses onto these qubits. And this is the Hamiltonian that basically encodes both the parameters that we can control about the pulses and how these parameters affect the rotation. So it is a question here just shows us that varying the amplitude, the phase, and the detuning, we obtain a rotation, like there's a passage from here to here, where we obtain a rotation about this axis here, that as we see has a 0z component, so it lies on the equatorial plane. And here instead we have an angle that is dependent on the integral of the amplitude. With this pulse, we obtain a rotation along any arbitrary axis, and which axis is dependent on the parameters that we decide. And the angle of the rotation is also a thing that we can decide. So on the paper are shown some algorithms that I wrote, which show better maybe the passage from one thing to the other. So it's just an assignation of parameters, basically, depending on the rotation that we want to achieve. Just that. Thank you.
Well, like in your experiment, it's like how you generated the data is using like, and then you're using the same circuit, and then you did kind of talk about this, like this is not cheating. But then, if say like we use another data set, and then what training answers are you going to use then?
Okay, yeah, of course the performance may vary, but the thing here is that it's equivalent of this, like it's like this. When we see that like the data is distributed in this way, we see this. So we kind of cheat by introducing a feature map that separates the data into this high-dimensional space, So I don't think that it's cheating, because we are just saying that we want to force the classifier to interpret the relationships in a certain way. But once we force those kind of relationships, it still has to figure out what to do with that. So how to classify them, So yeah, I don't know if I answered your questions.
This is like how would you design your answers, like if you're using the same like other data set, like some actual like not artificial design there.
Yeah. It has yet to be explored. I had the same thought about the IBM paper, so yeah. Thanks. Thank you.